This is the second part of our discussion on auxiliary power units, or APUs. Last time when we left off, we were talking about when they could be used. And so here's that APU operating charts that we left off on, showing different speeds and altitudes that the aircraft is operating at, showing that bleed air and electrical power can be supplied up to 15,000 feet with the ability to start engines up to 13,000 feet. Above 15,000 feet, the crew is only able to use the APU for electrical purposes, and that's up to 37,000 feet. If the APU is not running and the aircraft is above 30,000 feet, they would have to descend to 30,000 feet in order to start it, but then can go back above 30,000 feet with electrical power. So moving forward, looking at kind of what makes up an APU, there's roughly two categories. There's kind of smaller APUs and larger APUs. So we'll start with a small APU. And here we have a small APU. And these are going to be used to provide electrical power, and they're going to be used to provide bleed air to the aircraft. And so the way this is going to work is it's going to, first off, we're going to have an inlet to bring air in. Now this uses a centrifugal compressor and reaction turbine that are placed back to back. So here's the compressor. So air comes in through this compressor, or gets pulled into this compressor through the inlet. And after it goes in the compressor through the inlet, it gets sent out from the centrifugal compressor into the diffuser area. And we have essentially a reverse flow combustion chamber here. And it enters the reverse flow combustion chamber where air and fuel, or where fuel is mixed into it and it is ignited. And then after it leaves that area, it is going to, as soon as I can get my pen to go away here, it's going to go through the combustion chamber, and then it's going to enter the turbine where it'll expand. And that turbine is there to drive the compressor since they're piggybacked together. There's also a shaft coming off the turbine that is going to continue forward. And that shaft is going to continue forward through the center here and into the gearbox area shown here on the left. And that gearbox is going to be used to power the different items that the APU, to serve its purpose. So there'll be typically a 28 volt DC starter used to start the APU off the battery. There's going to be and the starter in this one is shown in the kind of the top area. There's going to be a fuel pump and fuel control to operate the APU, shown here. Kind of in the background here, it's got a shield over it, is a generator behind the fuel pump and fuel control. And so those are the main items that are going to be driven off of there. Some aircraft also will sometimes have a hydraulic pump driven off of the APU, although that's not particularly common. Or there'll be a small pneumatic pump used for something like maintaining head pressure on the hydraulic reservoirs. If we look at a larger APU, something like this still maintains, we have our air inlet. Now this one's shown on the top. And the air inlet still goes to a compressor, but in this case it's referred to as a gas producer compressor because this APU actually has two compressors, and we'll get to the second one here in just a minute. So the combustion section is behind us, so really not much different here. Now this one, instead of, this uses a axial type turbine, and which is located in the center of the reverse flow compressor. So reverse flow combustion chamber, excuse me, air is going to enter here. going to go through the compressor and then enter the reverse flow combustion chamber. And then it's going to make its way, through the turbine. And as it goes through the turbine, it's going to drive that turbine. And that turbine is going to, again, drive a shaft that's going to power that gas producer compressor, but then it's going to continue forward. And here we have a second compressor as well as the gearbox that we had on the small APU. So the small APU did not have a second compressor like this one does. And so that is known as a pneumatic supply compressor. So its job is, whereas the small APU, pneumatic pressure bleed air, let's go back to it, is going to be pulled directly off of the main compressor. And a larger APU, like the Garrett one shown here, the pneumatic supply compressor is going to be able to supply bleed air to the aircraft. And this one, this larger APU, you can see the kind of the bleed air path. So we have a bleed air duct coming down this way, and here's the end of the bleed air duct that would head to the aircraft. It also does have the ability to pull bleed air from the compressor, and there's a valve here in the middle, and then it tees together. So you can pull, with a large APU like this, bleed air can be pulled off of the, can kind of be siphoned off of the gas producer compressor, or it can come off of the dedicated pneumatic supply compressor, depending on the volume of air needed. On the accessory gearbox side of things, to the left, again, we have a DC starter motor. We're going to have an AC generator, and then a fuel control and fuel pump piggybacked on one another in order to supply the APU. But again, it'll start on DC to be able to use the aircraft batteries in order to start it. And then it'll have an AC generator to be able to supply 120 volt, three-phase AC to the rest of the aircraft. APUs are almost always, besides on some small regional jets, almost always located back in the tail. And then I say that the 727 had one located between the wheel wells, kind of in the wing root area. But here's a tail of an aircraft I've drawn in where the vertical stabilizer normally would be. And the APU lives in an area in the very back of the tail cone with a couple access doors. The inlet is going to be up here on the top, air intake door. It's usually a scoop style door with a plenum going to the inlet portion of the APU, and then the APU itself. And then the APU, the exhaust gases are going to go out through this duct that exits at the very, very tippy tail of the aircraft. And then the access doors at the bottom allow us to get here. So we can kind of see how this is located. Now this is why, like the 727 and some other tri-jets, they're not able to have the APU in the tail because there's an engine there, and so in that case they're put somewhere else. But almost all twin and four-engine aircraft are going to have APUs located back in the tail. So if we look at a small aircraft APU, this is off of a little turboprop. We can see this little one, and in this case, instead of doors, the entire tail cone's so small, the entire tail cone is removable. And here we can see the APU inlet kind of facing us right here, and the APU exhaust, which would come out the very back of the tail cone. This duct here you see coming to a vent. This is cooling air for the generator. So that's not the bleed air that goes to the aircraft. The bleed air that goes to the aircraft is actually on the kind of the opposite side of the APU. And on our accessory gearbox, in this case, there's going to be a generator, which we can kind of just see the black generator peeking out here on the bottom. Cooling air for the generator to keep it cool, coming out that duct I showed earlier. Back part here shows the combustion chamber. We can see the various fuel nozzles where they enter the combustion chamber here. We've got an igniter down over here on kind of the left side. And so that is going to supply that ground power and bleed air for the aircraft. Here's some larger aircraft. So we can see the APU inlet here at the base of the vertical stabilizer just below the rudder. You can see in this case it's a door that opens in, creates an air scoop for the inlet. And then the exhaust is this little circle in the tail. Or if we turn the aircraft and look at the back, there's an APU inlet door here, again at the base of the tail, and the APU exhaust at the very tip, the hole that's at the very back of the tail. On the CRJ aircraft, small 50-seat regional aircraft, they put the APU a little bit further forward. And so in this case, we have an exhaust right here that is on the side of the aircraft just below and inboard the right-hand engine. The inlet for this one is actually located, it's on the opposite side of the tail. And it's kind of located about in this region here, but on the left side of the tail. So we can't see it in this picture. But it's also a door that cants up and creates kind of an air scoop to be able to force air in flight or be sucked in on the ground. If we look at one of these, an APU that's actually installed in an aircraft, one that has the doors on the bottom, here you can see a view looking up. Now this is a larger aircraft, a larger APU. This is one that has a, excuse me, that has a dedicated pressurization compressor. And we can tell that because we have an air duct. So here's the air duct leading up to the aircraft, and we've got this T right here. So going straight up from the T is the pressurization compressor, and if we go back, this connects to the area where air can be pulled off of the main compressor. So this is one of those, the larger Garrett APUs. We can see our fuel pump, fuel control in this area. You can see the wiring coming in right here, and that goes to this black object, which is the generator. This other big set of wires here, they're going to route around and up, and they're going to the starter, which is above the fuel control in this case. And so we can't see the inlet here. The inlet would be on the top. We're looking up from the bottom, but we can see the exhaust duct going back into the tip of the tail over here on the left. This illustrates that the APU, and like all engines, is inside of what's called a fire zone. So we have here a firewall between the main part of the aircraft and the engine. Your engines that are mounted out on like wing pylons, those have a firewall in them as well, or just like a small aircraft has a firewall behind the engine up in the nose. The firewall is designed to be a fireproof barrier in case of an APU or engine fire to prevent it from being able to spread to the rest of the aircraft. And so the firewall here, this is going to be made from, it's usually not aluminum. Aluminum's not heat resistant enough or anything like that. So the firewall most of the time is either going to be something like stainless steel. Some are titanium, or can even be something like Inconel. But again, stainless steel and titanium are the two most common. And when the doors are closed here, so these doors that are, that are open on, you can see one at the top of the image, and you can see the door at the bottom of the image. When these doors are closed, they actually kind of create a seal. There's rubber seals around the edges. And so this area, if there is an APU fire, there's a dedicated fire extinguisher bottle for it that can fill this cavity with halon or carbon dioxide in order to extinguish the fire. And so by having the firewall there, it's going to protect the rest of the aircraft while we have firefighting equipment or firefighting medium that we can put into the area. So these ones that are mounted in the tail, to be able to remove them or install them with the technician is going to use something called, it's nicknamed a fishing pole, which basically is like a little cable hoist that can be attached. There you can see there's one attached on either side here. And these cable hoists are hooked to the top of the APU, and then the mount bolts are removed. And then you use the little hand crank to lower the APU from out of the tail area. So you'll see different versions of these depending on the configuration of the aircraft, or things like that. Control of the APU is very, very simple. Most of them just have the ability to be turned on and then start. This setup here works a lot like a key in a car. So the knob can be turned to the on position, which is the run, and that turns on, in most APUs, that's going to turn on a fuel pump, a DC powered fuel pump if one's not available, boost pump to get fuel up to the APU. And then it's also going to open fuel valves, that kind of thing. It's going to turn on the control computer, control logic board for the APU. And then the knob can be moved over into the start position. And the start position is typically a spring-loaded position, kind of like the key on your car when you move it to the start position. As soon as you let go, it's going to spring back to the on or run position. And that's where it'll remain as long as we have the APU running. And if we want to shut the APU down, then we just simply turn the knob back to the off position. You can see here there's an emergency stop as well. And the reason for that is if the APU is in the on position, and one turns it to off, it doesn't necessarily shut down right away. Many APUs go through some kind of a cool down or a preparation sequence in order to in order to properly cool the APU and get it ready to shut down so that it doesn't cause damage. And so if it was highly loaded, if the generator was highly loaded, or if a lot of bleed air had been used on it, many APUs will run upwards. Even once they're moved to the off position, they'll run at kind of idle for upwards of a minute before the APU actually shuts down. Whereas you can see the emergency stop here. An emergency stop will shut the APU down immediately. Essentially, it just closes the fuel valves to the engine and initiates an immediate shutdown in case of an emergency. But there is a risk that it could cause damage to the APU in the form of not being properly cooled down, or not being properly cooled down, or not being properly prepared for that shutdown and that large temperature change that's going to occur, during shutdown. For indication purposes, most APUs have very limited indication. In the vast majority of cases, you get an APU RPM indication and then a exhaust gas temperature, EGT, that's shown here. So this is one that's on ICAS, which shows APU, and this is also showing the different options. So under normal conditions, there'll be green readouts, but if the RPMs start to get too high, at 108, they'll turn yellow, 109%, they'll turn red. Or the EGT, the exhaust gas temperature, if it hits 985 degrees Celsius, it'll turn yellow, or if it hits 1035, it'll turn red. But for the most part, there isn't much you can do besides turn the APU on and off. And a lot of these too, if they have an exceedance like shown here, the APU computer will actually do an automatic shutdown. To see the control on kind of an overhead panel. So if we see the overhead panel for an aircraft, right here is the entirety of the APU control on this aircraft. It has an off, a run, and a start position, just like that knob I showed earlier. And then either like an emergency shutdown, or sometimes it's a smoke or a fire arm type button. Although oftentimes that's more centrally located with other fire handles and things like that. Firefighting for it is usually pretty rudimentary. It has a single button to arm the fire extinguisher, shown here. So in this case, a guarded button. You press it to arm it, and then press another button to extinguish. When you arm it, it not only does it arm the fire suppression bottle, but it also closes any fuel and air valves, hydraulic valves if you have a hydraulic pump, in order to isolate the APU from the rest of the aircraft. Fuel for most APUs comes from one of the main tanks, typically one of the wing tanks, and usually only one wing tank. And it often, the APU has a dedicated fuel pump, or it has a dedicated fuel, we'll call it a boost pump. in addition to the boost pump, there's the engine-driven pump that we saw in the pictures where I was able to circle the fuel control fuel pump. But we have a dedicated 28-volt DC boost pump located in the tank to move fuel to the APU, and that's going to run, that is DC, runs on batteries so that we can use it for initial starting before we have AC power available. And so when we go to start that APU, when we move that knob or that start button from off to the run position or the on position, any fuel valves that need to are going to open besides the one that allows fuel into the combustion chamber. So these are the fuel supply valves. The boost pump that's DC powered, that'll start running. And a lot of times it's going to run off of a dedicated 28 or 24 volt DC battery. Some share the battery, some have their own dedicated battery. When the switch is then moved to start, the APU computer or logic board is often, for the most part, going to handle the startup all on its own. And this goes back to even some of the oldest transport aircraft out there. So there really isn't much to do once you've moved the knob or the switch to the start position. All this stuff tends to happen automatically. So the air inlet door will open, the fuel valves will open to allow fuel to the fuel pump on the APU. The DC boost pump will start. The engine starter will engage to get the APU spinning. The igniters will come on as an ignition source. And then once it's reached what's called max motor and there's verification that ignition is on, then the engine fuel control will energize and it'll actually begin supplying fuel through the fuel nozzles into the combustion chamber, which will result in a light off. And once the APU becomes self-sustaining, then the starter and the ignition will disengage as the APU gets up to speed. So one way to look at it is something that looks like this, where it's showing the APU over time. And so what we've got going on here is this one now, instead of a dial that has a run and a start position, this one's got a kind of a APU power on button and then a start button, so two buttons. But in this case, the operator turns the battery on, the aircraft battery first. Nothing really happens yet. Then the power fuel switch is pushed, APU power switch is pushed, which is also the equivalent of moving the dial or a knob into the run position. That's going to cause the ECU, which is engine control unit, or engine control computer, to power up, and the inlet door is going to open. And then once the inlet door is open, then the operator will push the start button, or turn the knob to the start position. That will cause the starter to engage, and we can see now the RPM is beginning to rise right here. And once the RPM, in this case, now different APUs will have slightly different numbers, but once the RPM hits 10%, then the fuel solenoid is going to energize and ignition is going to come on. That's going to cause fuel to start flowing to the engine, which has air being pulled through by the RPM of the starter and the compressor. And then the ignition will ignite that fuel. It'll light off. We'll start to see a temperature rise at this point. APU will get to about 50%. The starter will automatically cut out. RPM's continuing to rise. And then RPM ultimately is going to reach right around 100%. Most APUs just want to get to 100%, and then they're going to stay there. And here now the APU levels off and the ignition automatically shuts off. The generator becomes available. Load control valve shows armed, and that means that the bleed air valve is armed to be able to open. And then the APU does like a built-in power on startup check, 4 seconds. That's showing 4 seconds after it reaches 99%. And at that point, the APU is up, running, and it pretty much is doing its own thing and can be used for engine starting. You can use bleed air from it for engine starting. Bleed air can be used for Environmental control systems, bleed air can be used for pressurization, and then the generator is used for power. So we just make that a little bit bigger so one can kind of see what's happening here. And then, for shutdown, the switch or the button is put back in the off position. APU will typically do a, kind of that shutdown cool down, and then upwards of, 30 seconds to a minute, then it'll actually shut down. And things like fuel valves will automatically close, the air inlet door will automatically close, and eventually the engine control unit computer will shut off and be dormant.